Good morning, everyone. Today I am going to present Unit 5 of Measurements and Instrumentation, which deals with the introduction of analog to digital converters. And ADC is an important electronic device that converts real-world analog signals into digital data that can be processed by computers, microcontrollers, and digital systems. In this presentation, we will discuss the need for ADCs, their working principle, types, characteristics, parameters, and applications. ADC stands for Analog to Digital Converter. Most physical quantities such as temperature, pressure, sound, and light intensity exist in analog form, meaning they vary continuously with time. Digital systems, however, can only understand binary values, namely zeros and ones. Therefore, an ADC acts as a bridge between the analog world and digital electronics. For example, when a temperature sensor measures room temperature, the output is analog. Before a microcontroller can process it, the signal must be converted into digital form using an ADC. Now let us understand why ADCs are required. Modern electronic systems are mostly digital. To process signals from sensors, analog signal must first be converted into digital data. ADCs enable digital processing of sensor signals, easy storage of measured data in memory devices, with reliable transformation of information. ADCs enable digital processing of sensor signals, easy storage of measured data in memory devices, reliable transmission of information through communication systems, interfacing sensor with microcontrollers and computers, automation and control in industries. Without ADCs, digital systems would not be able to interact with real-world physical quantities. This slide shows the basic block diagram of an ADC. The analog signal from a sensor is applied to the ADC input. Inside the ADC, the signal undergoes three important stages. Sampling, taking measures of the analog signal at specific intervals. Quantization, it is used to assigning each sampled value to the nearest digital value. Encoding is used to converting the quantized value into binary code. The output is a digital representation of a original analog signal which can be processed by digital circuits. ADC conversion occurs in three major steps. First is sampling. The continuous analog signal is measured at regular time intervals. These measurements are called samples. Second is quantization. Each sampled value is rounded to the nearest available digital level. This introduces a small quantization error. Third is encoding. The quantized value is converted into a binary number consisting of zeros and ones. Together, these three steps transform a continuous analog signal into a digital signal suitable for digital processing. There are several types of ADCs, each designed for specific applications. The common ADC types are flash ADC, successive approximation register or SAR ADC, dual slope ADC, counter type ADC, sigma delta ADC. Each type differs in terms of conversion speed, accuracy, complexity, and cost. The choice of ADC depends on the requirements of application. Flash ADC is the fastest type of ADC available. It uses a large number of comparators working simultaneously to compare the input signal with reference voltages. Because all comparisons occur at the same time, the conversion process is extremely fast. Characteristics of flash ADC include very high conversion speed, multiple comparators are required, higher power consumption and cost. Applications are radar systems, digital oscilloscope, video processing equipment. Flash ADs are preferred whenever high-speed conversion is more important than cost. Now let us discuss the successive approximation register ADC, commonly known as SAR ADC. This ADC uses a binary search algorithm to determine the digital equivalent of the input voltage. The ADC starts with the most significant bit and successfully determines each bit until the conversion is complete. Advantages are good accuracy, moderate conversion speed, low power consumption. Because of these advantages, SAR ADCs are widely used in data acquisition systems, microcontrollers, industrial instrumentation. Today, SAR ADCs are among the most commonly used ADCs in embedded systems. When selecting an ADC, several performance parameters must be considered. Resolution. It indicates the smallest change in input signal that can be detected by an ADC. Accuracy. It shows how closely the digital output matches the actual analog input. Sampling rate. It specifies how many samples are taken per second. Conversion time. It is the time required to complete one analog to digital conversion. Signal to noise ratio or SNR. It indicates the quality of the converted signal by comparing the signal strength with noise. Higher resolution, higher accuracy, and better SNR generally result in improved ADC performance. Resolution is one of the most important specification of an ADC. It is given by resolution equal to V reference by 2 to the power of n, where V reference is the reference voltage, n is the number of bytes of the ADC. For example, if the reference voltage is 5 volts and the ADC has 8 bits, then the ADC can represent 256 different levels. A higher number of bytes provides finer measurement and better precision. ADCs are widely used in many engineering and industrial applications. Some important applications are digital voltmeters for measuring voltage accurately, biomedical instruments such as EGC and patient monitoring systems, industrial control systems for process monitoring, communication system for signal processing, smart sensors and Internet of Things devices. Whenever analog information needs to be processed digitally, ADCs play a crucial role. To conclude, we learned about analog to digital converters, their necessity, conversion process, different types, important parameters, and practical applications. ADC form the foundation of modern digital measurement and control systems by enabling communication between the analog world and digital electronics. Thank you.